Alright, hell yeah. So I'm doom scrolling, and I might as well just make a video instead. And so we don't have any ice water, so we're just going to try to make this fast as hell. We'll see if that is even possible. But anyway, so we have material mechanics. This is James M. Gear, and we're continuing on column buckling. So let's go to that page, and booyah. So what we're going to have, and we're going to do the derivation. And just to let you know, it's going to be like a second order differential equation, and it's going to involve sines and cosines. And so we're going to try to explain why that happens. So hell yeah. So let's see where we want to start, because we do want to get, somewhere kind of decent, because here is the differential equation. So let's see if we can do this, because even if we get to, you know what? Let's just read through the pages. I'm so bad at this, but we're just going to do that because you don't want to read it. So might as well I read it and see if we can, not take too many tangents. Hell yeah. So we begin our investigation of the stability behavior, of columns by analyzing a really thin or slender column. And we're going to have pinned ends. That's going to be the first configuration. And why we're going to do that is because it's easy to check out the equations, anyway. So hell yeah, the status equations. So the column is loaded by a vertical force P that is applied through the centroid of the cross section. And anytime you see a figure, go to it and kind of study it. So we got figure 11.5a. So hell yeah, pin, roller, P is going straight through, and let's just do one at a time. So that was A. The column is loaded by a vertical force P. We saw that. That is applied through the centroid of the end cross section. And that's important. That first figure, there is no deflection, and so that force goes right through the center of the cross section. The column itself is perfectly straight. Oh hell yeah, people are liking my stuff. Alright, the column itself is perfectly straight and is made of a linearly elastic material that follows Hooke's law. And if it's just in compression, it's just going to compress like a spring. So we're going to see how it can get off kilter. For these columns, we've talked about how the reason it gets off kilter is because something pulled it laterally off kilter. Anyway, so since the column is assumed to have no imperfections, it is referred to as an ideal column. And we can even zoom in. So hell yeah, for purposes of analysis, we construct a coordinate system with its origin at support A. So it's probably going to be booyah right there. And then with the x-axis along the longitudinal. So that's kind of different. We're going to say, hey, this is the x-axis. And anytime you throw one axis on, you got to find your other one. So I do the right-hand rule. Do like the karate chop, or do your four fingers in this direction with your palm facing this way. And then you're going to roll your fingers into this direction, and that's going to be x to y. And as you roll your fingers, your right hand, your thumb is going to point out of the page. And so they're probably going to talk about that. So hell yeah. So the coordinate system, yeah. So with the x-axis along the longitudinal axis of the column. The y-axis is directed to the left in the figure, and this is where you can use right-hand rule. The z-axis, not shown, comes out of the plane. But I always do that. Fingers in the x, roll into the y, and then that gives you your z-axis. All right, especially if you're going to use, if you're going to do any cross products, you have to have you can't have your axes backwards, else you're just making up, an extra negative somewhere in the cross product that you're not going to be able to figure out. Anyway, so we assume that the xy plane is that plane of symmetry. So in the page, that's the direction things are going to squish out. And so that's the plane of symmetry, and that's what we're going to say in the column, and that any bending takes place in that plane. So now we're going to see figure 11b. So when it gets bent, it's going to bend about this, if we're looking at a sheet of paper, just the page, and so it's not bending out towards us. Cool. The coordinate system is identical to the one used in our previous discussions of beams, as can be seen by rotating the column clockwise. Yeah, so the coordinate system is identical when we use beams by rotating the column clockwise through an angle of 90. Okay, hell yeah. So that's what we're going to say. It's like this is just like a beam got bent, but then, we just rotated it clockwise. But keep that in mind, because if I have the tradition of just like, hey, this is the x coordinate, positive in that direction, and this is the y coordinate, I would be rotating this thing down that way. And then so this is where I kind of got confused. This is actually bent in a frowny phase. That actually is a negative moment, because that's what got me tripped up, because the next thing they're going to show is this moment diagram, and they're always going to put the moment where it makes it positive. So you can see that this frowny face is made by a moment going the other direction, but we always put the positive direction on. And so, yep. And so that's kind of interesting. But interestingly enough, they don't put the positive direction. Axial tension should be positive. This is showing axial compression. So, leave it to textbooks to, yeah, and that's something you shouldn't be messing around with. You should be totally, every student is just going to get messed up, if we don't over-explain the sign, what do you call it? Anyway, moving on. Just the usage of sign convention. That's what I was looking for. Cool, so the coordinate system is identical to a beam just 90 degrees clockwise. And we can see that ours, I'm not going to go back to it, but yeah, is a frowny phase if we do that. So when the axial load P has a small value, the column remains perfectly straight. So that's what we're going to say. Like, this always just remains straight until it undergoes direct axial compression, just like a spring is being compressed. The only stresses are the uniform compressive stress obtained from the equation, hey, the compressive or normal stress, which has units of force divided by area, is just that equation. It's just the force divided by area. You know what I mean? Cool. The column, and in this configuration, the column's in stable equilibrium. We don't have any bending, bowing, or buckling. So which means that it returns, oh, well, yeah. So what they're saying, back up to this sentence, it says when the load is, because to actually make these scenarios, because previous to this, and we should go back, we were making this setup like the 2 bars with a really stiff rotational spring. So when you do apply some sort of change in angle to this spring, hell yeah, it wants to spring back. And then so one way to look at this is this spring is just hella stiff. And so, and it's not that this force P is pushing on the spring. Hell no. It's that you're applying a load, hanging some sort of weight, and then you are actually pulling this, so it's like, for this diagram, you are the external force pulling this column. You're the act of God that happens in a building that's just like, hey, I'm going to shift this column this way. But that's going to require a hell of a lot of force if this spring is hella stiff. This load then, is in kind of a place to actually drive it farther. But like, you provided that heavy load to pull it outward. And so that load is wanting to spring back. And so so when you do let go of the load, this force does nothing, and it just returns to a straight position. But then you get into a critical place where maybe you design this column where this spring you didn't get the stiffest spring. And then so when you actually pull it out this far, this load is really, really heavy. So that's the other envisioning thing. You want to make this load really heavy. And then the returning force of this spring is just not very good. And so you're the one pulling it out. And in that scenario, you have to pretend like you're pulling it out and keeping it there, and then all of a sudden letting go. So it was never a stable equilibrium. To keep this in equilibrium by pulling it out by that act of God, you actually had to pull it out and then maintain force this direction just so it doesn't collapse. And so so that is critical to the assessment of beams, because that's what we're doing. And it's saying, hey, when we apply some sort of little force, even if, so this is the act of God, something actually pulled sideways on it, we get this bend to happen, and then we let go of whatever, force we're pulling sideways. So they call the disturbance in the force. And then it just returns, because this beam is just a hella stiff spring. You can imagine this beam is just like one of the stiffest bow and arrows. This is the bow, and it's a beam. So if you use a beam as a bow and arrow, or a bow, hell yeah, you'd be pulling, yeah, it's a hella stiff spring. It's going to spring back. So that's what we have going on. Hell yeah, so that's pretty good. Now we can kind of move on. So yeah, so this says when that axial load is small, the column is in stable equilibrium, which means that it returns to the straight position after disturbance. And I wish they even said that sentence reverse, being like, hey, when you disturb the column. And I guess they've been talking about what the hell the disturbance is, but I think they could do a better job of really dialing that in, because that wasn't too clear for me the first go around. Okay, so for instance, if we apply a small lateral load and cause the column to bend, see, they talk about that more. The deflection, after you let go, after the disturbance is removed, the deflection will disappear and the column will return to its original position when the lateral load is removed. So cool, that was kind of the first take home, but that was kind of from last video. We want to get into some of the equation-y stuff. So as the axial load P is gradually increased, we reach a condition of neutral equilibrium. Yeah, so we remember we talked about how the spring is so stiff, and then maybe the spring isn't very stiff and the load is huge and it's going to collapse. Well, there's going to be some place where, like, hey, that spring is moderately stiff and that load is moderately decent. And so when we do pull it sideways, it's going to be in a neutral equilibrium. And the reason from that was the equations of equilibrium. Both the restoring force of that spring in that kind of that ideal condition where you have a column as two pins with a spring in the middle. That spring torque is a function of the angle. And then so is the load. So is the torque, or the collapsing torque due to the load. And so we can kind of come back up here is that, this is the better one to look at that. So what we have is like, hey, if this part of the beam rotates this direction and rotates flat, we have a collapsed beam. And so this spring wants to rotate it back to vertical. And so we talked about in the other video that if you apply a moment, it doesn't matter where you apply a moment on a rigid body, it's going to rotate. Well, I don't want to get into that. But anyway, so this moment's going to try to rotate this thing back vertical, and then this load separated by this distance is going to try to make it collapse the other way. So what is this load making collapse? It's because it's providing a torque, which is a couple, or it's providing a couple. And that's the torque. It's two forces separated by this distance. This distance is going to be a function of half the length times sine of this angle. And because the angles are really small in these, what caused it doesn't take too much of an angle, but we're going to say that sine theta is equal to theta. So this length is just, instead of half the length sine theta, it's just half the length theta. And that's going to be this distance. The force is P, so the actual torque is just one of these forces times that distance. So we have P half the length theta. So that torque is a function of theta. Same with this spring. This spring is going to be a function of theta. In this, the moment of that spring is going to be some sort of stiffness times theta, and it's going to be linear. Linearly increased theta, this spring linearly increases in moment. And so that's why when we pull it out, there's going to be some place where it's balanced. It doesn't matter if we pull it out just a little bit. The angle that's causing the torque to increase linearly is the same angle that's causing the moment to increase linearly. So when we apply a little bit of angle and then double it, both of these scale evenly. And then so, cool, we have this perfect weird load on that we can just move this thing out to here and it's just balanced. And so that's kind of weird and creepy because people are going to die anyway, because it's not going to take too much more load to just kill everyone. All right, hell yeah. And then so here's the equation for that. So you use this, which is, and you do free body diagram. You sum the moments about B. It's going to be the moment at B, which is the spring stiffness times the angle. The angle that forms is actually this used to be 180, and now it's this crunched in angle, which this whole triangle, like if you consider this a triangle, has 180 degrees, this triangle has 180, and then it got reduced by 2 theta. See how all the angles in this triangle had to be 180, minus this theta minus that theta. So this change in angle from there compared to here is 2 theta. So that's where you get the moment. is the moment due to the spring is 2 spring stiffness times 2 theta, and then the moment, or the couple caused by this load, these two forces separated by this distance, is, what did we say, half. And that's going to be, and if we use right hand rule, use our right hand to rotate this way, our thumbs into the page, that's going to be a clockwise rotation. And a positive rotation due to the spring is going to be counterclockwise. So right hand rule, thumb out of the page. And so we come down to here, our moment equation. We're going to sum the moments at B. We have moment at B positive minus that couple, which is the load, and then half the length times the angle. But we can see that this is going to be the spring stiffness times its angle, but this angle formed was 2 times the angle. So we have 2 times the spring stiffness theta minus this load half the length theta. And then both are a function of theta. And again, I wish they had one more line here just to show that, hey, this aspect had theta in it and this aspect had theta in it, and then you factored it out. I think that would be more visually pleasing to me. But here you're just going to have to say, hey, I can factor this theta into both terms, and so both were a function of theta. So it doesn't matter if I double theta. If both of these terms are equally balanced, then we have no net torque. And so when we do disturb it, so there you go. So that took forever. That was pretty decent. Getting better at kind of explaining that. And so when we do have this act of God pulling out, cool. The restoring moment of the bow, we talked about bow and arrow, of this beam is going to want to restore it. But this load is now having a force that, so if we take the moments about A, we're going to see that we have P times this distance. And that's going to be a moment that causes it to rotate more this way. So if I take just this is kind of like that ideal, chunk of beam. If it rotates that way, it's going to flatten and pancake and buckle. If it rotates back vertical, hell yeah, that's kind of what we want. And so what's creating it to rotate back vertical is this moment. But that's where they have just the positive moment on here. But we know that the moment generated by bending a beam this way is the opposite. Because to bend a beam this way, we actually, and again, put this x-axis down, and we have, if I had my y-axis and x-axis, this beam would be bowed upward, which is a frowny face, which means that on both sides of it, we had to apply a moment this way and this way. So if this is a little chunk of that frowny face, to get this frowny face, I need to take that moment and apply it that way. So the arrow is going tail to tip. And but in this diagram, they're just showing the positive moment. But that's where I'm just like, this is kind of bunked up because they're not showing positive axial tension, which, you know what I mean? And that's a sign. Well, are they showing? And they're not showing. I was thinking if they're showing shear, but no, this is axial tension. This has nothing to do with shear. There is no shear forces on something in pure bending. So they just kind of. I think that's a faux pas. That they could have showed this in axial tension, and just knowing that that's going to be negative. I mean, why put this in compression, seeing like, okay, it's positive, and then have this moment, and then just throw in the moment being like, oh, sign convention says this is the positive moment. Well, you know what I mean? Well, just draw your sign convention so it's always the positive of both, and not. So that drives me crazy, because no student is going to be like, oh, I know exactly what's happening right there. You know what I mean? And so, all right, hell yeah. Cool. So, yeah, where are we at now? So now we have, as the axial load P is gradually increased, we reach that neutral equilibrium. So that's what we did a pretty good job of explaining, and I think that was important. So in which the column may have a bent shape. The corresponding value of this load is the critical load, P, and the spring force doesn't change in the beam. It's linearly elastic. It's a function of its material. But this load, you can make this load meet that. You know what I mean? So think about that. This load, you're reaching a critical load. At this load, the column may undergo small lateral deflections with no change in the axial force. And that's the act of God. Anytime they're talking about lateral deflections, you are putting an external force to actually do that. It's not the driving force down. From the column, from the ideal situation, that column should just be in axial compression. You You know what I mean? So you are applying that small lateral deflection. And with that happens, we have no buckling and no restoring force. And when you think about this small lateral deflection, you have to say you are deflecting it, and it takes a force to do that. You're pulling it because you're moving mass, let's say, but then you're holding it in that location, and then you're let going, and then you're seeing what happens. And in that case, it statically stays there. So for instance, a small lateral load will produce a bent shape that does not disappear when the lateral load is removed. So that's just another way to say it. Thus, the critical load can maintain the column in equilibrium either in the straight position or in a slightly bent position. So hell yeah. And then just know, like, hey, that's your factor of safety. You better not get to that critical load. People are going to die, obviously. It'll take one little feather of weight to just bring down the whole system. All right, so at higher values of the load, the column is unstable. And so now we're talking about, it's like, that's where you're just like, well, what are you talking about? You just said that if we reach that critical and anything greater, it's going to collapse. But that's only if you apply that kind of act of God force sideways and that lateral displacement due to things that happen in buildings. If you don't apply that, we're still saying that the column can take axial compression, but that load is unstable because the second some sort of act of God comes in and moves that column sideways into this configuration. That's where these diagrams kind of mess you up. The column is always like this until some sort of act of God force pulls it this way and then says, all right, I'm done pulling it this way, or I'm done pulling it this way and actually resisting it back to hold it in place, because you can have that. You can have a force that pulls it but then actually kind of rigidly holds it into that place. That makes a stable connection. No, but then the second you release that, you know what I mean? Because if I pull it this way and it does want to buckle and it's in stable equilibrium, I would have to be putting a great load this way to keep it from buckling. So that's where also it's not just something pulling it this way, it's something actually displacing it. So I think that's good to know. It's like we are physically displacing it. Think like a huge giant that can just move it. It doesn't care what it feels like between its fingers. But then once it lets go, oh hell yeah, then you're going to have a collapse. Okay, so that's what we're going to talk about. So that's the unstable equilibrium. The column was just normally just taking a really high load, but it was totally straight. And let's see how they explain it. But it may collapse by buckling. That is by excessive bending. And they really don't even talk about it. They don't even talk about, hey, an external disturbance pulls it sideways, and then obviously the torque due to the load outdoes the torque due to the bow characteristics, that resisting spring moment of the actual beam. So for the ideal case that we are discussing, the column will be in equilibrium in the straight position, even when the axial force P is greater than the critical load. So this would be kind of cool to set up columns where you get a higher load and then you just go push on them and then they instantly collapse. However, since the equilibrium is unstable, the smallest imaginable disturbance will cause the column to deflect sideways. And so that's cool. And once it does deflect sideways, then you have a runaway train, because that load based on the angle that gets created causes the moment. That moment's always going to be bigger than the restorative spring the spring force of the column being bent. So once that happens, the deflections will immediately increase and the column will fail by buckling. The behavior is similar to that described in the preceding section for the ideals buckling model 11.2. And so I think we talked about that because that was this model right here, is that you provide the act of God and then let go, and this load is creating a torque this direction that's bigger than this weak spring, which is the property of just the characteristics of the beam or the column. And so it can't restore and it collapses. Okay, hell yeah. So where are we at? Yeah, that unstable equilibrium, that was figure 11.2. The behavior of an ideal column compressed by an axial load P may be summarized as follows. That load can be less than the P critical. No one dies. The column is in stable equilibrium. If it gets jarred to the side, it returns to a straight position. So the column is in stable equilibrium in the straight position. And that's what they're saying. It's in stable equilibrium. That's why you can move it to the side and it still stays stable. It goes back and restores. If the load is right at that critical point, I mean, you're never going to see that. Either people died or like, I mean, no one's going to be like, oh, look at that bridge, it's moving that way. Or look at that column, I mean, it's bowing that way, hella, and then everyone's still on top of, whatever. And then everyone's just happy. Hell no. But this P-critical is, that column is in a neutral equilibrium in either the straight or slightly bent position, and it can move through that bent position. Something like an act of God can move it to a different location and it'll just remain there. It's not wanting to collapse and it's not wanting to restore. And then we have, total failure. Where the load P is bigger than that P critical, the column is in unstable equilibrium in the straight position and will buckle under the slightest disturbance. Of course, a real column does not behave in this ideal manner because imperfections are always present. For instance, the column is never perfectly straight and the load is not exactly at the centroid. Nevertheless, we begin by studying ideal columns because they provide the insight into the behavior of real columns. And now here's where I'm exhausted. I don't want to do this anymore, and it's just because we're up against differential equations. But I do want to read through this because I think we can. And, and we're just going to go through and solve, and we're going to read, damn it, look at this. And we're going to read to at least to here. Right to where we get to the critical loads. I think if we read to the actual bringing up of the differential equations and solving for C1, solving for the constants. No, we have to read through the critical loads because we have to solve for C1. And is that where we solve for the constants? Okay, hell yeah, I think we can do it. I don't want to, you know what I mean, because it's difficult. But I think we're pretty good on this. At least for the first go-around. So differential equations for column buckling. To determine the critical loads and corresponding deflected shapes for an ideal pin-end column, figure 11.5a. So we got to look at these. So there's your figure. Whoops. Where are we at? Okay, hell yeah. So the figure is below us. And we use one of the differential equations of the deflection curve of a beam. Now, these equations were in Chapter 9. I'm not going to go thumb back through there because, I hardly, when I see an equation like this, I'm just like, it's so hard to wrap your mind around. But these equations, that's another proof that if you can go through that proof and you can see it, good for you. That's amazing. So these equations are applicable to a buckled column because the column bends as though it were a beam. So hell yeah, and I'm pretty good at beam bending. I kind of understand that. So let's read this. Although both the fourth order differential equation, so this is a second order differential equation, meaning that we have deflection, and we have deflection with respect to the change in x. And so let's talk about that. Even though we're vertical, here's if I come out to this distance, let's say I came out a distance x, here's my deflection. And let's say I change my x in the positive, what happens to my deflection? My deflection goes down. So that would be the first differential equation. From at this point, let's say right here, I'm going to have a negative change in the slope. So if I increase in the x direction by 1 unit, my deflection, that's v, that's just this distance, goes down. It's not as much. And so that's the first derivative. The second derivative says, okay, from here, let's say from this flat spot to here, it went down, but is it going down? And and I think it's easier to make bigger slices. So from here to there, did it go down very much? No, but it did go down. So I'm going to say, hey, from here to here, that first derivative, the change in the deflection as I move in a change in x, hell yeah, it went down a negative a little bit. And now from here to there, look, from same distance maybe, change in x, and it went down, it started to go down hella. It went from here to all the way there. So if I divvy this up into halves, if I change my x this amount, hey, this deflection decreased by a little bit. If I change that x another amount, whoa, this deflection decreased more than half, and basically, so that was a bigger change in deflection. So if I say what's the change in the, how do you say that? So this first was just the change in the deflection. but I want to know how the change in the deflection is changing. You know what I mean? I know there's a negative change in deflection. Cool. Is it getting more negative? And yes. So at this midpoint, it's getting hella more negative. Over here, it's getting positive, but here it's getting less positive. So I was over here, like this is my chunk. Whoa, we increased a lot. So from halfway, we increased a lot in the deflection. But then from here to here, we change x again, and we didn't increase very much. So the change in the increase, that positive increase is getting less. So I have a negative value on the rate of change. Yeah, and it's just like, oh man. And the second you actually say it technically, it's like everyone lose their friggin' mind, man. So cool. So that was good enough. You know what I mean? Differential equations. I think it takes a life of, because even if you know exactly what's happening if you're the smartest person in the room, you're going to have the hardest time like just relaying that to anyone. And so I think we do a pretty good job. Hell yeah. So then it says that both the fourth order, and was that even for fourth order? No. Like, so that was, the first one was deflection. The second one was the rate of deflection. That's the first differential equation. The second differential equation is so the first is the slope of this line. The second is the change in slope. And so that's what we have. The moment generates a change in angle, a change in slope. But then if you have a change in slope, the third equation is, oh, bummer. I'm kind of, what is the third, maybe it'll say. So although both the fourth order differential equations, the load equation, and the third order differential equation, the shear force equation, are suitable for analyzing columns, we will elect to use the second order equation, the bending moment equation, because its general solution is usually the simplest. And I gotta take a break. Alright, hell yeah. So we got some ice water. We're gonna do round 2. We're gonna pump this out. So I'd have to go back and be like, what's the fourth order? What's the you know what I mean? But yeah, oh yeah, because shear, like the actual, you know what I mean, to actually find the deflection is going to be, yeah, like what is that? The deflection, although both the fourth order differential equation, the load equation, so is it saying that this is a fourth order with respect to the load? I think that's kind of what it's implying. Don't quote me on that. But anyway, cool. So I'd have to go back and review that. But anyway, I think we explained why. Well, we explained what a second. You know what I mean? It's the deflection is changing. You know what I mean? Maybe it's going more negative, and the second order is that it's like, oh, it's getting more and more negative, or it's getting less and less positive. We kind of showed those two cases. So we use the second order equation, the bending moment equation, because its general solution is usually the simplest. The bending moment equation is EI is just the material property. I think I-beam. E, I don't know, just think another structural shape. But E is its stiffness. E is the modulus of elasticity, but it gets kind of bizarre because if E gets really big, I mean for steel, it's 29 million. For wood, it's 1 million, you know what I mean? And that bigger that number, the more stiff things are. And that means that, yeah, they're just stiffer. It takes more force to deflect them. So hell yeah. So those properties, if those are a stiff material and the I-beam, this I is moment of inertia, and it's just a well-designed I-beam, that's going to be very large. So let's look, I mean, even simple equations, it's like, okay, let's say I provide a moment to that beam. I have some sort of number over here. E and I don't change. Like we made the I shape of the beam. You know, think moment of inertia I-beam, and then we gave it material properties. We made it out of steel. So this isn't changing. So if I say a moment of like 1,000, and well, let's just talk about it. Like if I just give this to be just a normal number for the moment that's causing bending, this number is already huge. And then so this deflection has to be really small. And that's what you see in beams. Maybe this deflection is just millimeters of deflection, where your bending moment might be, I don't know, maybe we're generating 10,000, whatevers. But this number put together is going to be, like I said, E could be 29 million, and the I-beam, in inches, because E would be 29 million PSI, pounds per square inch. I can be up to like 70, I think, I know just a 2x2, it's 0.4 just for the 2x2 really thin stock tubing that I get out of steel. That's 0.4. And so, hell yeah, for a big old I-beam, you can get up to, just for something simple, you can easily get to 20, I think 20 to 80. I know the S, the I and S, those varies. I'd have to look them up. But anyway, so just know that I have a bigger number. Let's say I have 100 million here, and then I put in 1,000. And so, this number is going to be really, really small. I think we got it. Hell yeah. So that's that equation. And so it's in which M is the bending moment at any cross-section. And I don't know, like what causes bending? I think you want to think about it as pure bending. If this is a ruler and you go put a moment on A and a moment on B, that's going to be pure bending. And that's what we have. We have no shear in this because we're applying all loads axially. And even though we do get this deflection, the deflections are really, really small. So we'd have no shear stress. And so this load right here, this at point A, if we did a free body diagram, A would have a pin connection, so we have an upward force and a horizontal force. But we don't have any horizontal forces. All loads act perpendicular. And sure, this is right at the center. If we take the load right at the center, it's acting perpendicular. But if I come down here to this cross section, it seems like it's going to be acting at this angle, and it does. But we're going to say the deflections are so small that it's almost like it is always acting. Wait, but that's counterintuitive, because if we do say we're going to deflect it, we have this load P that's straight down, and then, that's kind of interesting. And I think we get that from this upper free body diagram more than anything. If I chop this and just do the upper part, I only have a downward force at P. And then so when I chop this free body diagram, at this, I can have a shear force, I can have a axial force, and I can have a moment. And so, and especially if I just chop it perfectly in the X, in this direction, parallel to the Y-axis, then that face is going to only see a down, if I'm just taking this chunk, and I drew it right here, I'm going to have an upward load to resist this, but I do have a difference that load is offset, and then so that's going to cause a torque this way. I have to have a restoring torque, and that's going to happen internally on that cut. And so hell yeah. And those are going to be statically balanced if we have, only if we have that P critical. But I think that's also a good place to be like, okay, if I got that load critical, it's going to be balanced because the properties of the beam are restoring the force. P is just critical where it's actually wanting to buckle it the other way, and we have that balance. And that's the only place where you're going to have like a statics problem. Else, the act of God pulls it out, lets go, and then you have a dynamics problem. It's either moving back towards straight, or it's killing everybody and collapsing. Okay, sweet. I'm going to drink some more water. All right, hell yeah. So in that equation, we have in which M is the bending moment, and we can't get both the equations, but there's the equation, EI, second derivative, which is the change in the, what do we call this? The deflection. So we have change in the deflection as we change X, and then we're going to have a change in that change. We have a change in the change in deflection as we change in X with respect to X. So it's a double derivative. Second derivative of deflection with respect to position along that axis. So I think we did a pretty good job. I think anytime that you get a differential equation, walk your way through it by saying, hey, pick a value right there. I'm going to change my x. What the hell happened? Well, the deflection changed. Okay, negative. Okay, now do x again. The deflection changed again. It changed more. So therefore, the difference in the change, the second derivative, is a bigger negative number. Okay, sweet. So moving on. So m is the bending moment at any cross-section. V is the lateral deflection in the y direction. And we're going to say, we've already said, like, hey, this is positive. This is a positive deflection. So just in the books, when you have like just the normal sagging smiley face beam, that deflection is always negative. Sure, your beam is smiley facing, your bending moments are positive, but your deflection is now downward in the downward y direction. So this is a negative moment causing this. Right hand rule is but think about this. If I take my right hand and sweep it this way to try to get this, that's not how we determine positive bending. Positive bending is like if I have a section, to actually get it to bend, I have to apply a moment this way, and then I have to apply a moment this way. Both of those, you can't use your right hand rule because both are different directions. But we're basically saying, hey, that's causing it to smile. Well, this is a frown when we have this is our x-axis, this is our y-axis. So draw this, rotate it 90 and just draw it like this, and we have a frowning face. The y-axis is up, the x-axis is that way. And they told you to do that, but, without reiterating it 5 or 6 times, I don't think you're going to really be able to see that. I didn't see that the first time, be like, oh yeah, that's an obviously negative bending moment, or it's a frowning face, and so I couldn't see that the first go around. Okay, so hell yeah. So V is that lateral deflection in the y direction. In our case, it's positive, which is associated with a frowning face. And the EI, we talked about that, flexural rigidity. And so that is a definition. They're going to say, hey, E times I is now a term called flexural rigidity. And we talked about how E is modulus of elasticity, but as it gets bigger, you get more rigid. It takes more force to make things, that's Hooke's law, where it's like I have a really stiff spring, it takes more force to make that spring change in length. Cool. And then flexural rigidity for bending in the xy plane. Everything happens in the xy plane. The bending moment M at distance x, and that's where it looks like they chose it at the halfway point. That's also, I would think, a faux pas, even though that's the place where it's just like, yeah, that looks like the force is totally vertical. They didn't, I don't know. The angles are really small, so everything is vertical, basically. Even though you displace this a small angle, it's imperceptibly vertical. That's kind of what they're getting at. So that's why it kind of is a good choice to put this x at the middle, but you could have chose this x at any location and still have a downward force P, and then, and only a downward force, where if I took the reactions at A, I'd only have an upward force. I would have a torque causing this thing to, this little piece to actually flatten, that's the buckling, due to that load P coupled with the same load at A with that distance between them. And then the restoring moment, it's drawn, as it would be positive, causing this thing to smiley face. Obviously, this thing is frowning face, and this moment should be the other way, or it's just a negative of the way it's drawn. It's drawn right here as how it should be for positive moment. If I actually did this moment, this thing would smile like that. Cool. All right, so the bending moment M is, so we're saying that bending moment is a distance x right there from the end of the buckled column is shown acting in the positive direction. So there you go. But they should throw big red flags or just make this in highlighter because yes, it's shown in the positive direction, but it says note that the bending moment sign convention, and it doesn't even say that, cool, we drew it in the positive direction, but this is actually negative bending moment. But it just says, note that the bending moment sign convention is the same as that used in earlier chapters. Namely, positive bending moment produces positive curvature. And one way to look at this is once you define your x and y axes, your x is the vertical upward, and so if you see a frowning face, that means your curvature is negative. And one way to look at that is like this is creating a circle, and the distance to the radius, you would have to move in the negative y direction to get to that center. So the center of that circle is down here in the negative, where if I have a smiling face, then the center of curvature is positive. The center of that circle is in positive. So that's more of a technical way to look at it, and that's why they said the curvature, if you have positive bending, the curvature is positive. And the center of that positive curve will be in the positive x direction. All right, sweet. So bending moment sign convention is the same as that used in earlier chapters. Positive bending moment produces positive curvature. The axial force, P, acting at the cross-section is also shown in figure 11.5c. So we're going to talk about that. Let's see what they say about that. It says, since there are no horizontal forces acting at the supports, there is no shear forces in the column. Therefore, the equilibrium of the moments about point A, we obtain, so cool, no shear forces. So we're just going to sum the moments about point A. This P is offset, so it's going to be some distance. That's going to cause a moment. Right-hand rule, a positive moment. This bending back is going to cause a negative moment. So that's what hopefully we see from this equation. We have a, but they just show that positive moment just being positive. But obviously this is a negative value. And then we have P, PV, which, I mean, the way they have this drawn, P would just be a positive value. So yeah, all sorts of like, what are they doing to us? So it says from the equilibrium, moments about A, we obtain that the moment, and I guess just the way they drew it, if I'm just assuming this is the direction of the moment and this is P, both are right-hand rule this way. So cool. So I'm going to have M plus PV is equal to 0. But if I rearrange and get one to the other side, I'm going to have the moment is actually the opposite of the force and the deflection. So this force with this distance is causing it to rotate that way. The moment has to rotate it the other way for this thing to maintain equilibrium. So that's the equation for equilibrium. So, and then where V is the deflection at the cross section. This same expression for the bending moment is obtained if we assume that the column buckles to the right. Okay, so hell yeah. So if I move this column buckling to the right, the load P is down, I'm going to have a negative, P times that distance is going to be a negative value, negative PV. But they're going to say that V is also now negative. So I have a negative P, negative V. They're probably going to do that, which is absolute madness. And then they're still going to say the moment is the other, positive. So that's hopefully what they do. Yeah, that's what they do. They say we have moments positive, but we have a negative P and then a negative V. So we get the same result. But that one is a humdinger to actually. So cool. This same expression for the bending moment is obtained if we assume that the column buckles to the right. So this is how it's buckling to the right. The deflection is a negative V. That's what they show here. When the column deflects to the right, the deflection itself is a negative value. But the moment of the actual axial force about point A also changes sign. So the moment of this force P also changes. And so thus the equilibrium equation for moments about A is just M minus P times negative V. So it's just M plus PV, the same thing, which gives the same expression for the bending moment M as before. The differential equation of the deflection curve now becomes, because we have this, and this is probably the part where it's just like, well, I guess, we have moment, and this is moment as a function of x, because we took some just random point x, and we have a tendency for that portion to actually, we're hoping it's stable, but here's the moment. This is the moment. This is yeah. Let's see if we can actually figure out. But yeah, they're gonna throw that equation for the moment. Yeah, what is this? So if I do see some deflected shape, then the moment generated in that beam is going to be a function. The moment at any location, so this location X, and we can come back to here, is just like, well, maybe we are in the center. So actually, either side, I don't have any change in, so that's going to be 0. So I don't have any change in the deflection. But if I go this direction, well, I do. I have a change. The change in deflection is negative, and if I go a little bit farther, it's increasing. So this second, so if at this location P, I'm going to have a positive number. I mean, a negative number that's going to be bigger than other locations, maybe. Well, actually, it's going to be that value right there, and it's actually going to get bigger and bigger as we go this way. If I go this way, if I started here, and then I'm actually increasing. And so, so if I was just before this, I would have a positive first derivative. I'm increasing. The change in the deflection is positive. But the rate of change, actually, we're getting more positive, but we're actually getting, we're getting more positive and then less positive and then less positive. So that rate of change is actually negative. So yeah, so that value is going to be negative. And you do have a continuous, I don't know if this has to be continuous or not. But you have, so you have a negative value for all purposes. Like here we have, well, let's do this. So from here to here, the deflection actually increases substantially. But then from here to here, the deflection doesn't increase substantially. So the second derivative is going to be negative. And what we're going to find is that we have a big decrease from here to here. We have a big decrease in that change. But from here to here, I have hardly little increase. And then from here to here, I have hardly little decrease. And so, oh man, I'm getting whooped on, working. But that's what I try to do every time, is just like, well, let's talk through the differential equations. But hell yeah, let's just throw m in and we get this, and here's our differential equation. And then you just say by solving this equation, which is crazy because no one even talks about hey, let's play around with this, first. But booyah. So this is going to be second order differential equation. Let's just, this first go around, let me just read the words and then see if we can come up with anything. So by solving this equation, which is a homogeneous, need some water, linear differential equation of second order with constant coefficients, we can determine the magnitude of the critical load. See, I'm just spacing out, but we can determine the magnitude of the critical load in the deflected shape of the buckled column. So that's where, so we're going to solve this, and we're going to get a solution that's going to say, hey, we're going to get a solution based on the critical load and the deflected shapes of the column. Let's see if we can do that. So note that we are analyzing the buckling of columns by solving the same basic differential equation as the one we solved in Chapter 9 and Chapter 10 when finding beam deflections. However, there's a fundamental difference in the two types of analysis. In the case of beam deflection, the bending moment M appears in equation 11.3 is a function of the loads only. It does not depend upon the deflections of the beam. So our equation is being like, hey, we are going to deflect the beam out. Is that kind of what we have? In the case of buckling, the bending moment is a function of the deflections themselves. That's kind of the act of God part. So we have, the only reason this is actually, going to fail is that something deflected it. So this part of the equation is probably the difference between the other equations from the other chapters. And, I don't know, like all differential equations, as long as they have a solution, cool, but it just sucks, I don't know. It just sucks when they have the form of C1 sine, something x plus C2 cosine. But this is going to be the, just jumping ahead. This is the solution. This is going to be the deflection at any value of x. So any value of x, I'm going to throw a value of x in, and I'm going to get a deflection. So we can even talk about that because, it's good to see, like, because this is where I'm okay at doing this. Because if I say, hey, this is my x value, at x is equal to 0, there's 0 deflection. So now let's go back to this differential equation. If I throw in x is equal to 0, well, sine of 0, this sine of 0 is 0. And then cosine, if I throw in 0, is going to be 1. So if this is 1, and then the deflection is 0, well, that means that 1 times C2 has to be 0. So C2 has to be 0. And so I'm sure it says that somewhere like right there. So hell yeah, C2 has to be 0. And then if we, what are the other locations? And then so the other aspects of a sine and cosine is when x is equal to, well, and that's where they're going to get into it. This is an angle in radians. And if it's 90 degrees, is that what you say? You know what I mean? If you have sine of 90, this becomes 1, and this becomes 0. And so if this value right here, kx, becomes like that 90 degrees, which we call pi divided by 2, then this becomes 1, and then the deflection, yeah. But, yeah, and I think we just need to read more about that one. But yeah, we got the first one down. That was pretty solid. And then we kind of understand from a word-based perspective of saying, like, hey, this is different because we are actually providing the deflection, and that comes into our equilibrium equation. And our equilibrium equation is a differential equation because the value for that moment is a function of, let's read this. The value of that moment at that value x is a function of the material properties and the rate of change. And I think I could explain that in the next videos because we have molecules that are getting bent, and the moment is going to be the change in the angle. If I just have if I have a continuous arc, like a continuous circle, then, now let's not get into that. I'll lose my mind on the differential, but I do want to get more juiced up on that. Hell yeah. So now, note that we are analyzing, where are we at? So we talked about how that is a function of v. In the case of buckling, the bending moment is a function of the deflections themselves. Thus, we now encounter, I'm going to move it up, a new aspect of bending analysis. In our previous work, the deflected shape of the structure was not considered, and the equations of equilibrium were based on geometry of the undeformed structure. Yeah, so that is kind of cool, because you're just like, oh yeah, all the stuff we did in statics was just like, hey, we're not assuming the structure deforms at all, because once you say we have forces and then things did change shape, well, cool, go change their shape and then run the statics again and you'll get different numbers, and you kind of have to iterate back and forth to actually kind of find a stability point. And so we have now, however, the geometry of the deformed structure is taken into account from writing the equations of equilibrium. And I do kind of like this one because the whole aspect is having that act of God actually provide that disturbance and that deformed shape. And then having this equilibrium that's either going to fail or restore or reach a critical value. And then from this proof is the only place where it does reach equilibrium is where it is perfectly, where that P is P critical. So throughout, P is going to be P critical, and then because that's where we're going to, if this is equilibrium equation, this P is P critical. And maybe it's a general P because they haven't put the subscript P critical, so sometimes I kind of get ahead of myself on that. All right, so here's the solution of the differential equation. For convenience in writing the solution of the differential equation, we introduce the notion. So, where are we at on this? Because if I have EL, let's say I divided everything by P. I'm going to have EL divided by P. And then I'm going to have this P divided by P, 0 divided by P. So it's just going to be this EL divided by P. The second, and I have a hard time even saying this, the second derivative of deflection, and then plus V. So if I divide everything by P, that's what we're going to get. And then they're going to say, hey, P divided by, bummer. Yeah. But for this, they're going to have, they're going to introduce, so that was EI divided by P. But then they're going to say P divided by EI, and the square root of that is K squared, or where K, so K squared is going to be P divided by EI, even though, we can see, at least we can divide this by P. But we're going to define this as a parameter. And you do that just because based on the solution, and it's going to explain it. But hell yeah. So if that's K squared, and then so K is going to be the square root of P over EI, in which K is always taken as a positive quantity. Note that K has units of the reciprocal of length, and we can talk about that. This is force. This is force per area, so the area pops upstairs, that's a length squared, and this is length to the fourth. So we're going to have divided by length to the fourth, and then, divided, we're all said this is going to be a divided by length squared, right? And then, so if K squared is divided by length squared, K is just inverse length, reciprocal of length. Hell yeah. So K has units of the reciprocal of length. And therefore quantities such as Kx and Kl, which we'll see in our differential equation, like right here, Kx, are dimensionless. And that's what we need for sine of angles. They're dimensionless. And so non-dimensional. So using this notation, we can write equation 11.5 in the form of this K squared. And so that's kind of fascinating that, so here you go. So K squared is P divided by EI. So I need this term right here to be P divided by EI. So my bad, I did it the opposite way. Instead of dividing everything by P, my bad, you divide everything by EI. So this, and that makes sense. So you get your second order differential equation just by itself. I think that's that seems to be important. My differential skills aren't the best. But so I'm going to divide this by EI, and this divides by EI. And then I'm going to say P divided by EI is K squared, where the square root of P divided by EI is K. So that's how they do that. And then so now here is the differential equation. And I think you need this K squared. You say this is K squared because the general solution is just in form of K. And instead of just saying this was K and this is the square root of K, I think that would have been probably a better way to do it, because why overcomplicate it and introduce the K squared? But anyway, so that's just the way they did it, and they get this general solution. You just know that you could do it whatever way you want. This is just a constant, and you could just write it out. Just write those. K is square root P divided by EI in that location. So from mathematics, and that's where even in these textbooks, they're not going to hold your hand. They just say, from mathematics, we know the general solution of this differential equation is this. And that is the hardest leap for me, just to be like, okay, I get something that looks like this, and then I get something that outputs like this, and it's hard for me to see the tangible nature. But we did show that, hey, when x is 0, this is 0, and our deflection is 0. And the other place where our deflection is 0, we can talk about this now, because our deflection, when we throw in x is L, our deflection is also 0. And so let's throw that into the equation. When x is L, I'm going to have KL. Let's just read this to see what they do. All right, so here's your general solution. We have two constants, and your constants are based on the from the boundary conditions. So this says, and this equation is the deflection is the constant 1 times sine kx plus constant 2 cosine kx, in which which C1, constant 1, and constant 2 are constants of integration to be evaluated from the boundary conditions or initial conditions or end conditions of the column. So note that the number of arbitrary constants in this solution, 2 in this case, agrees with the order of differential equations. So I guess that's just a property of differential equations. If you have a solution and it's second order, you're going to have 2 constants of integration. Also, is that what they call them? Constants of integration. Also note that we can verify the solution by substituting the expression for the deflection into equation 11.8. So yeah, so what they're saying is that, well, no, they're saying the opposite. They're saying this equation I can differentiate with respect to x. So I can say, what's the derivative of the deflection with respect to x? And then I can use kind of the chain rule. This is going to be u substitution, sine u, the derivative of sine u. It's going to be the derivative of sine u, du, dx. And the derivative of du, dx is, I think, what is it? I always forget. But anyway, was it like 1 divided by k? So we have 1 divided by k, c1 sine, and this goes to cosine. Cosine goes to negative sine. But anyway, you do that twice. You can take the second derivative of this and then throw that value into here. That'll be a good homework assignment for me to do after this video. And then throw in this value for v into here. And then everything will cancel. So that's kind of fascinating. So that will be a solution. That's what they're saying. And that just says, also note that we can verify the solution right here by substituting the expression for v. I think that's a very important part, especially when general solutions to differential equations look drastically different than the differential equation itself. I think that's one of the hardest things about learning about differential equations. To evaluate the constants of integration appearing in the solution, we use the boundary conditions at the end of the column. I found one, but the easiest one. So namely, the deflection is 0 when x is 0. So we talked about that. And the deflection, and it's also deflection is 0 when x is L. So here we have these 2 conditions. The first condition gives C2, and they don't even explain it. You know what I mean? Holy hell. So when we throw in x is 0, this term goes to 0, this goes to 1, and we have the deflection 0 is equal to C2, so C2 must be 0. And then when we get the second condition, where C2 is equal to, that's where C1, yeah. So the first condition gives C2 is equal to 0. Oh, and therefore, yeah, so we're using both of those. Yeah, that's fascinating. So once we found that C2 is 0, we're just left with this equation. And then we're left with, well, now I'm going to plug in. So that was something I couldn't, there's no way in hell I would have been able to, you know, figure out the logic on that. But now that we know our equation is reduced to just the deflection is just C1 sine kx, when I throw in L here, this has to equal 0. So I have C1 sine kl has to equal 0. And that's the bread and butter of this, I think. Yeah, because that's the second constant. And then so we have this, C1 sine kl is equal to 0. And then from here we have a product of 2 things is equal to 0. So we do have a trivial solution where C1 is 0. And so from this equation, we conclude that either C1 is 0 or that this sine KL, and K is a parameter, it's a function, so K, just don't forget, is, hey, material properties and that critical load. So now we have the juice of this. It's just kind of in the form of something that's, you know, signs are repeating or kind of, you know, yeah, like a circle. But anyway, so if this part of the equation is 0, then we also have a solution for, so that's for the equilibrium. Yeah, so this general solution of deflection holds when, yeah, this constant 1, what does it mean? Constant 1 can be anything as long as, I don't know. But yeah, so that's another way to get this to be 0. But then what? What the hell does that mean the C1 is equal to? So from this equation, we conclude that C1 is either 0, or C1 could be anything, but then the sine KL has to be 0. We will consider both of these possibilities. All right, so we have case 1. If the constant C1 equals 0, the deflection is just 0. V is also 0. That's going to be the probably trivial case. And therefore, but this is where the column remains straight. Okay, fair enough. So in addition, we note that C1 equals 0. Oh, yeah. Because if both are equal to 0, then it doesn't matter where we are along the length, there is no deflection. So think about that. If C1 is 0 and C2 is 0, I mean, we basically have just 0 the entire length. So it doesn't matter where we are along the length of this, along the beam, we have no deflection. So that's where, I'm glad I'm like trying to pick it apart and then read it, and then it kind of makes more sense that way. So hell yeah, remain straight. In addition, we note that C1 equals 0. Equation D is satisfied for any value of the quantity KL. So consequently, the axial load P may also have any value. This solution of this differential equation is known as the trivial solution. But that is important because P can have any value. And I think they should have wrote this general solution actually with, where do they actually write it with all the players? And they really don't. That's a bummer. You know what I mean? They don't write this general solution with K. You know what I mean? If you actually threw this in here, it would be kind of cool because then you could see that if C1 is 0 and C2 is 0, then the load can be anything, but that's still satisfying equilibrium. We got this general solution from an equilibrium equation, and the load can be anything because our constants of integration are 0. So that's going to, obviously, the load being hella huge is going to be that unstable equilibrium. And then they're saying that's mathematically the trivial solution is represented by the vertical axis of the load deflection diagram in 11.7. So hell yeah, and this is the diagram of stability points. This is equilibrium. So if I have a huge load and the beam is straight, there is no deflection, cool, I can be way heavily up here and we're just in unstable equilibrium. And so this is, to read this diagram, I would say like, hey, you provide the act of God. If I'm up here and I take the beam and move it sideways at that same load, we're going to have a collapse because that location is outside equilibrium. And anytime you take this at this load level and then you move outside this line, it's either going to do two things. It's either going to collapse or it's going to restore back to 0 deflection. So if I'm down here, stable equilibrium, the loads are real small, and I have that act of God moving the whole column sideways, this is going to restore back to there. And so that's where we get this line. If that load is right at the critical value, where the bowing properties, the restoring force, kind of the spring moment of the beam itself, can only restore as much as the load is. And those are both a function of kind of the deflection. So as the deflection doubles, both of those doubles, and they're balancing perfectly. So I can have the act of God move that beam sideways, and we're just chilling. You know what I mean? The beam isn't buckling, but it's not restoring. But obviously everyone dies in that scenario as well. But cool. But we have to use that neutral equilibrium, for our general solution. And I guess not. I mean, that's where I just said, hey, no part in this general solution did you have this P be P critical. This P can be anything. So I have to catch myself all the time on that. We just said that if C1 and C2 are 0, P could be anything. And it's still going to have 0 deflection, but it's going to be represented by an unstable piece of equilibrium. So hell yeah, so that's figure 11.7. It gives the behavior of an ideal column that is in equilibrium. It's either stable or unstable in the straight position, no deflection under the action of compressive load P. Case 2. The second possibility for satisfying that equation is get equation D. So we can come back up here. This is equation D, where we have this is 0. We need to figure out our constant of integration. But this part, constant of integration could be anything, and sine could be anything. So maybe let's talk about that, because if this value is 0, well, then this term goes to 0. Yeah, that's still, yeah. Well, and our constant of integration over here is 0. Yeah, so we're still equilibrium. That's kind of confusing me, but hell yeah. So we still have, so let's just read on and see if we can kind of crack this. So case 2 is where this is equal to 0. The second possibility for satisfying equation D is given by the following equation known as the buckling equation. Oh yeah, and I kind of remember, is like, cool. I think they really need to write this equation with these values in here, with this k being right there. Because if I am saying that this side of the equation is 0, well, the only way this side of the equation is 0, if the thing in here equals 0, but it can't equal 0. Well, the load could be 0. Cool. Then it's 0. But that's a nonsense value. That would be like the trivial nonsense value. Mathematics has that trivial solution, but that's if I throw in this value for k in here and then say the load is 0. Well, this is always, sine of 0 is always going to be 0. So then we need the next value where this part of the equation actually becomes 0 again. And it's when this inside becomes pi divided by 2 radians. And so it's a dimensionless term, and that's what we use radians for. It's also dimensionless. And so when this equals pi divided by 2, hopefully I'm getting that right, because that's 90, right? Pi halves, pi, you know what I mean? And then 2 pi for a full circle. And so yeah, so when this value, so now we have when this value gets to pi divided by 2, this becomes 0. So, and then that's going to be, and this, like this part of the equation don't change. Again, it's just what it's made of. But this is the load. That can change. And then the distance x, from 0 to L can change. And so that's what we're going to have. So we could have a larger distance. And that's tripping me up right now, because it seems like, well, what if it seems like the halfway point's where you're going to have the biggest deflection. Oh, but they're saying the deflection is 0 anyway. So yeah, so I am going to throw in L in here as the length. So that is fascinating. So we are still saying that the entire length of this, I can be x is equal to 0 or x is equal to there. And this is the structure, that we're showing, which is represented by this solution. Yeah. I get that it's sines and cosines, and you kind of have those shapes. That's all. That's kind of where I'm at on that. So yes. So this value is going to reach. So if x is L, that part of the equation is going to be the bigger part. And then k is going to be this part of the equation. And let's just get rid of the square root and just pretend it's kind of a linear. So I'm going to have a value for x and then a value for p. And if my value for x is L, or the largest it can be, then the value for p is going to be the smallest to get this to be that pi divided by 2. Once this is pi divided by 2 at that distance L, that's where this is going to be p critical. And because this is the equation for the beam from any location of x, then that's going to be the most critical value. So I'm going to say from their derivation, p critical is where x is L, and then this part of the equation where I have this square root p divided by EI times L is going to equal pi divided by 2. So let's see if that is the case. So we have sine KL. Oh, and then why are they saying it's just pi? Did I get that wrong? Sine of 90. Is 90 pi? No, that makes no sense. Oh, no, sine of 90 is 1. So my bad. Yeah, so that's just a huge... So sorry, I've been just kind of going through this and just totally realizing that, no, sine of 90 is 1. Sine of 180 is 0. So that is a simple mistake, but that's a very... I hate mistakes like those because it seems fundamental to be like, whoa, like that obviously is going to give you a trash answer. And it's just real easy to mistake. To be like, no, this is going to be 0 at angle 0. At 90, it's going to be 1. And then at 180, it's also going to be 0. So when I throw an L in here, and this is square root PEI, it's when this is equal to pi. Not pi divided by 2, but pi radians. That is going to be where this is P critical. Cool. And then they're going to go into the other ones where, well, what if this value is equal to 2 pi? Well, if I have length here, and then this is the square root, and then forget the square root. If I have length and p is equal to a number like 3, cool. Length don't change, and the number 3 don't change, and then so p is that p critical. But now let's say I increase this 3 to 6. Now I have PL is equal to 6. Now my p critical can half. No, it can double. Sorry about that. See, that's where... So if I have PL is equal to 3, that's this whole idea of, you know what I mean? PL is equal to pi, and I'm really simplifying this. I'm just saying that, hey, let's just say this is P, and then X is the L, which is the biggest value of X you can have in the column. So I have PL is equal to 3, and pi is 3. And then I can double pi to 2 pi, and then I have PL is equal to 6. So the P critical can double. And so that's what they're going to say in the literature, that we're not worried about the other nodes, I think they call them nodes, or solutions to this equation. We're just worried, and we're not even worried about the first one. When X is 0, or when X is L and P is 0, that's nonsensical. Like, obviously, there's no load on it, so it's not going to buckle. But it's that first node. So that's where you get that part where we have sine KL, is that aspect, is when this is 0. And now we can disregard the sine part because it's just when the inside hits 0, pi, or 2 pi. We talked about that. 0 degrees, this is sine of 0 is 0. Sine of 180 degrees, that's pi, is going to be 0. Sine of 2 pi, full circle. You're just basically saying sine of 0 at that point. And then it'll say, however, since KL is equal, oh well, they're going to do the first one. KL is equal to 0 means that P is 0. So this solution is not of interest. And this is fascinating because that's why textbooks are so fast. Every line is like, what the hell are they talking about? And so I like to talk about it first and then read the textbook. And I think I do a pretty good job. I'm actually, like, this is tip-top for my, like, education and teaching ability. So I'm really, this is great. I'm really appreciating this video. Drink some more water. Yeah, and there's two things I want to do. I want to learn how to teach, and then I also just want to learn how to learn this stuff, because I swear, at the end of the day, like, sometimes you have to care less and to be like, I don't understand it, just give me the friggin' equation and move on. But the fact that I am able to sort through these proofs is just like, well, why not? You know what I mean? But it takes 2 hours here, 2 hours there. And like I said, I don't have this fully down. Every time I go through this, I find new pieces. And the crazy thing is like, going through this stuff, you can make just bad assumptions. You can assume they're doing it one way, and then you just assumed horribly wrong. And then it takes a while to reread it to be like, oh, I see what they're talking about. But we're doing pretty good on this. Okay, so hell yeah. So that's the solution that is not of interest when P is just 0. That, it's nonsensical. Therefore, the solution we will consider are when KL is equal to some, if this is pi, 2 pi, 3 pi, That's the values we're interested in. But still they're going to say, hey, 2 pi is not of interest, but we'll hang with them. Instead of just KL is equal to pi, they're going to say KL is n pi. And then so we're going to, so there you go. So that solves that aspect. And yeah, where did they go? So see equation 11.6a. All right, so yeah, 11.6a. And where are we going to apply that? I don't get how they just jump to, so we have P is equal to this. Therefore, the solutions, I guess we have, what, 2 solutions? Oh, man, do I have to pause this? I don't get where, I sometimes I have a hard time being like, what are we even talking about now? But this was a function. We said KL is equal to 0. So right here we have KL is equal to NP. And that's why they need to do 2 more steps in this book. I mean, we just talked about what the hell K was. It's the square root of P divided by EI. It's that critical load divided by, just the construction of the beam itself and the material it's made out of. So let's see if we can, intuit. This is the square root of P divided by EI is equal to N pi. So what they're trying to do here is get P by itself. So again, K is the square root of P divided by EI. So I'm going to take L to the other side, and then I'll have N pi divided by L on the other side. I'm going to take the square root of both sides. So then I'm going to have N squared, pi squared, L squared. Those where those terms come from. And then I still have P divided by EI over here. And then I'm going to have to multiply EI up there. But that's crazy. They don't even show you what K was within this. But I mean, I guess you could just see it. It's on the other page. So that's horrible. No, I mean, I can't say stuff like that because I really enjoy this textbook. It's just really good. But I love when I can kind of see stuff that, like obviously textbooks are very difficult to read because you're just like, whoa, they went from here to here and I almost lost my mind. I was like, I don't even see that. But now we have this P critical. And again, we don't have to use N is equal to, we can just use N is equal to 1. So remember that? N is just 1 pi. So I can say that P critical is just pi squared EI divided by L squared. And then so let's see what they do with this. This formula gives the value of P that satisfies the buckling equation and provides solutions other than the trivial solution to the differential equation. The equation of the deflection curve from equation C and then E is, now we have V is equal to C1 sine kx because C2 is 0. But now I have C1 can be any value and then sine of and so here's the that's crazy because we were solving for boundary conditions, so that makes sense. We were trying to say, hey, when V is 0, what are these constants? And then we found from this solution that this constant can be anything because what we're going to say is when sine is kx and where this value k KL. And that's tripping me out. Okay, so yeah, then they're doing 2 things here. When this value is KL, then it's 0. But in our original equation, we want this equation to be anything. So we're going to have, that's why you have this. You're basically saying it's KX. How do you say that? Yeah, you're basically saying it's KXL. So that's what this is. This is XL. And then if you throw in the value of L, is that right as well? Because if this value is K... but they're also... How did we do this? We said when KL was equal to pi. So when this value was equal to pi radians... Yeah, oh man, this is driving me crazy. So if you see it, cool. But I at least have that where if I throw in the value of L, I'll have 0 deflection. And we're saying that this can be anything. So when I throw in this value of, I see it now. If I throw in x is equal to L, the L's cancel, and let's say n is just 1, I have sine of pi, and that's 0 now. So that's where this equation is. Cool. And so only when p has one of the values given by equation, let's read this. So by this equation, only when p has one of the values given, it is theoretically possible for the column to have a bent shape. For all other values of p, the column is in equilibrium only if it remains straight. Therefore, the values of p given by this equation are the critical loads for this column. Yeah, so let's read that again. So for all other values of p, the column is in equilibrium only if it remains straight. Oh, so that is fascinating. So yeah, only when p has one of the values given by equation. Oh, it's hard to read. All right, I got to come back to that. I kind of get it, but here's your critical load. So they say the lowest critical load for a column with and why do they call this the lowest critical load? Oh yeah, it's the lowest. It's the least amount of weight before this thing's going to buckle. So yeah, and we talked about that. The lowest critical load for this column with pinned ends is going to be attained when n is equal to 1. So we're going to go back up to this equation. When we throw n is equal to 1, that's going to give us our value for p. And so now p critical is pi squared EI divided by L squared. And the corresponding buckled shape, sometimes called a mode shape, is going to be the deflection, is going to be C1 sine pi XL. As shown in figure 11.8b, so we should probably go to these figures. So this is 11.8b, and this is where it has this shape. The second node is where it looks like this, and the only way you're going to get it look like this is if something's kind of holding that position. But it's just fascinating that if something is holding that position and it's still free to make this shape all on its own, you can double that, no, the deflection is n squared. So now we have 4. This is 4 times as strong, and your P critical is a function of 4. But somewhere right in here to here with this deflection curve, I'm sorry, I'm apologizing, I'm not quite getting it, but I'll have to do that for another video to be like, because just what they're saying in here, I'm just like, I can't do it, I apologize. All right, hell yeah. And so yeah, that's going to be the lowest, and we have P critical, and then here the corresponding buckling shape is going to be this. And so this is where if I do throw L in, I'm going to get sine of pi. It's not 2 pi, so this is the first, the corresponding buckling shape. This is the mode shape. And that's going to be that first figure. The constant C represents the deflection at the midpoint of the column and may have any small value, either positive or negative. Therefore, oh yeah, that's fascinating. So if I throw in L divided by 2, then I do have 1 here. Okay, yeah, so there you go. So yeah, because we were doing the boundary conditions when sine was, when x was L. When x was L, we have sine of pi, that's going to be 0, is going to make your deflection 0. But then as we just travel halfway, we're going to have L divided by 2. So I have L divided by 2 divided by L. That's pi divided by 2. That's going to be 90. That's sine of 90. So that's where we're going to see the most deflection. And that deflection is this value C1. And so the constant C1 represents the deflection right there. So that's what they have, C1. When you have more nodes and it's supported, that's going to be your value for C1. Cool. Therefore, the part of the load deflection diagram corresponding to P critical is a horizontal straight line from 11.7. Thus, the deflection at the critical load is undefined. Or what are we talking about? Didn't we just talk about that? Okay, so let's read this. So the constant C1 represents the deflection at the midpoint, because we talked about that, of the column and may have any small value, either positive or negative. Therefore, the part of the load deflection diagram corresponding with P critical, yeah, so there you go. So, and that can have any small value, actually. So that is this location. That is in neutral equilibrium. Because our equation, we took our equation from equilibrium based upon this idea that P critical makes the moments, balanced. And we had a differential equation. We were trying to solve for it. So that P critical is where C1 can represent any value or any movement of C1. So yeah, so that's, again, the act of God thing. We can move this value of C1 anywhere, and it'll stay there. So it's not just, it can be a changing value at that equilibrium. But this equation does give us this value of P critical, and obviously we can set factors of safety to be lower than it. So it says, thus the deflection at the critical load, yeah, that deflection C1 is undefined. So C1 is an undefined constant of integration. Although it must, and so I'm so glad I got there. So although it must remain small for our equations to be valid, and that is true. We're saying that those loads, like the deflections are real small, we're using small angle approximation. Above the bifurcated point B, the equation is unstable. And below point B, it is stable. So we're going to go back to this column. This is the point where the load becomes unstable, where if we do have a slight deflection, then we'll buckle. And that's the bifurcation point B. Buckling of a pinned column in the first mode is called the fundamental case of column buckling. The type of buckling described in this section is called Euler buckling, and the critical load for an ideal elastic column is often called the Euler load. The famous mathematician Leonhard Euler, 1707 to 1783, generally recognized as the greatest mathematician of all time, was the first person to investigate the buckling of a slender column and determine its critical load. Euler published his results in 1744 by taking higher values of the index n in those equations. We obtain an infinite number of critical loads and corresponding mode shapes. The mode shape for N2 has two half waves as figured in this figure. 11.8c. The corresponding critical load is 4 times larger. So you get a critical load that's 4 times larger because your n is squared. Your 2 is squared. Then the critical load for the fundamental case right here. The magnitudes, and so why even take that into consideration? Maybe there's some cases where you're just like, hell yeah, we had the column and we actually braced it right in the middle, so then it's it kind of fits this pattern. We just kind of pushed the material up against it, but it was still free to bend about that point. It wasn't a rigid point holding that column. Cool, so the magnitudes of the critical loads are proportional to the square of n. Yeah, and so that's how if this n doubles, it's the square, and so the critical load quadruples. And the number of half waves in the buckle shape is equal to n. So if I have n, I'm going to have 2 half waves. N is 1, I'm going to have 1 half wave. When I square n, I'm going to get that is going to be how the multiple of the critical load. And I think we did it. So buckled shapes for the higher modes are often of no practical interest because the column buckles when the axial load P reaches its lowest critical value. The only way to obtain modes of buckling higher than the first is to provide lateral support of the column of intermediate points, such as the midpoints of the column shown in figure 11.8. See, I'm just spacing out now. but it says the only way to obtain modes of higher buckling than the first, is to provide those lateral supports. So I did talk about that. That's the cool thing about reading textbooks for the second and third time. Like, try to envision what they're going to say. So if I do have some sort of lateral supports here, it's still able to freely pivot about that point, then you're going to induce those higher loads, those higher modes of those higher modes. Enough said. And then, so the only way to do that is to provide lateral support of the column at intermediate points, such as the midpoint of the column, and that's what we see in that figure 11.8. All right, hell yeah. And then, so I think I'm done. You know what I mean? I'll just kind of show you these general comments, 3 seconds on this, and then if you want to read, about those. But I think we did it. I think I actually got through there. There was kind of that one piece that I'm going to go back to, but I think we kind of covered that, because C1 is undefined constant of integration. Because it's a point of equilibrium, we can move that C1 to any, that's kind of that act of God moving that column. And if we are at the critical load, it's not going to buckle. And so this all comes from this, this ideal case where we have the column acts as a spring, that when we do have deflection, that spring is ready to restore it to vertical. And so that's what most columns do, that stay upright, is that spring is hella stiff. And if something does shift the column to the side, that act of God, sure, you have that load that's creating a potential to buckle, but this hopefully is restoring that. And so, and booyah. And we used the second order differential equations, and we went through that whole process. And so at that critical load, though, where you can move this and it just stays put, therefore that C1 was this deflection, because we had a function of that general solution was deflection is C1 plus some sort of sine plus C2 plus sort of some cosine. We were easily able to find that C2 was 0, but the fact that if we do induce deflection, that has to be represented by that equation, and that is going to be that value of C1. And so there you go. And that deflection can be anything, but has to be relatively small from our assumption that when we take this distance, we're taking the sine. Basically, it should be sine of the angle. So if you do the sine of the angle, then, sky's the limit. It doesn't have to be small, and you can get that differential equation ain't going to work. That differential equation only works probably if you use that small angle approximation to get. And that's what differential equations are. Like, some that actually work are just very crispy. And anything that gets more complex than that, sometimes you can't find a crispy little solution. So just keep that in mind. All right, I am done. So thanks for joining me. Hell yeah.